We now wish to graphically add vectors by the method that was used by sailors and people to sail the ocean long, long ago. So the first thing we're going to do is we're going to start by drawing our first vector. We're assigned a couple of different vectors in this problem. One is 5 meters is 60 degrees. And we're going to start by going to the origin and drawing to scale a vector whose length is 5. Now, obviously I'm not going to draw it actually to full scale of 5 meters because that's larger than 5 yards. It would go across and out of my office and on into the hallway. I'm going to scale it by some ratio. For instance, 1 centimeter on the paper might represent 1 meter, in which case I would draw this 5 centimeters long to represent 5 meters. Or I might use 1 inch to represent 1 meter, in which case the arrow would be 5 inches long. You could make it something else. You could make 10 centimeters equal 1 meter, in which case it would be a 50 centimeter long arrow. But you do this based on the size of your graph paper, and by using a ruler and drawing it to scale with a protractor, you can then measure the result with your ruler. Alright, so I don't have a ruler in this film, but I'm at least going to show you the steps. I'm going to start by going and attaching the origin, and I want to go out to about 60 degrees. That's 90, that's about 45. I'd have a protractor here, and I would measure that angle with respect to the x and make sure, for instance, that it was 45 degrees. And that would be my first vector. So if you walk along here, you will have completed step A. Let me put a little arrow here and note that that is vector A, and that this is in fact 60 degrees, and that this length is 5 meters. Now, when you add vectors, the vectors have to have the same units, just like anything else that you're dealing with. You can't talk about how far did you walk. You say, oh, I walked 5 meters at 60 degrees, and then I walked 10 meters per second at 40 degrees. That makes no sense. What's 5 meters plus, 10 meters per second? Doesn't make sense. It's like adding apples and oranges. So both of these units, if they're going to be added, they have to have the same units. This one does. It says 4 meters at 90 degrees. Now, we walked from here, say our campfire, down to here. Well, that's our new starting point. So if we go up here, you could think about there being a new axis like that, and like this there. And so everything we measure now is going to be with respect to this new axis. Well, my second arrow, this guy right here, if you would, let me do that. This guy B is going to start with the new origin right here. And it's going to follow this, 4 meters. It's going to go, if you, like I said, used an inch or whatever, and you're going to do it at 90 degrees with respect to this. So 90 degrees, not with respect to the initial location. Do not go off 90 from there. It's always with respect, unless it says otherwise, from the direction, the positive x. Alright, so this is my new positive x. So it's 90 degrees, so it'll go straight up. So in this case, we would walk it straight up. I'd measure and make sure that was 4 units. Like I said, don't have a protractor on this computer, so like that. And that's B. Now what A plus B means, it means do this first, that's A, and then do B. So where are you going to end up at? Well, you're going to end up right here. That's where you're going to end up. And the question of A plus B means if you went like a crow flies in a single direction, straight across, how far would you have to travel and in what direction? Well, we'll draw the A plus B in blue. And let me start here. And I just draw it right to there. That's what I would have to do. So that would be A plus, plus B. Now, what could I do? Well, I could find this angle with a protractor. Call that angle alpha. I could find that angle. And I could measure this length with a ruler. This length would give me the magnitude, and that angle, which is more than 60 degrees but less than 90, would give me this angle that I need, and then I would just write the length followed by the angle. And that would be the end of the problem. People have been doing that a long time. Now, what this brings up some interesting questions is, can you flip the order? Is A plus B the same as B plus A? Now, you may say, well, of course it is. It's always been like that, man. I warn you, when you said a course back from elementary school, you were talking about scalar math. There are other things in the world besides that. So the question is, do vectors obey the same rule that scalar math does, that you can reverse the order in which you add things? And the answer is yes, they in fact do that. If you're very careful, you can prove that, in fact, using this right here. What you can do is go the same distance up, like this. See if I can do this carefully. Whoops, didn't. And again, you want to do this to scale to prove it, and I'm not, so I might have a little drawing error. You want to go like this. That would be B. And then you want to add A. And so this would be your new starting point. And if I did this right, it would go right over there. So in this case, what I've done, I've said B, and then I did the operation A, and to get from here to there, I'd still draw the same blue arrow, but now it represents B plus A. So what we just shown is that B plus A is equal to A plus B. And so when you go from your house to Walmart, for instance, it doesn't matter which of these two operations you drive, you can get to be at the same place. You could go, for instance, north and then go at an angle, or you could go at the angle and then go north. Either way would work. So this is a neat thing. It tells us that, like scalar math, vectors can be operated in different directions. There are quantities, for instance, in rotation, that do not obey this, and therefore, when they're macroscopic, are not truly vectors. This is a consistent. Or for it to be a vector, I said some things have direction and magnitude, but really not vectors. Well, that's right. If they don't obey this law, then they wouldn't be. All right. So this is important. They have to obey this law in order to be considered a vector. So this is just the statement below that I put in a box. Graphical methods prove that A plus B is equal to B plus A.